Light-emitting diodes by Gabriella, Genesis, Alex, and NG High. Table of context. First, we're going to explain what LEDs are. We're going to give examples of LEDs, the scientific background, the science LED colors, how it relates to quantum chemistry, and then our conclusion. So first, our introduction. What are LEDs, or light-emitting diodes? An LED, at its most simplest definition, is a device that can emit light when a current flows through it. In more specific terms, an LED is a semiconductor chip that is positioned onto a reflective surface that will produce a light when a semiconductor receives electricity. This type of light that gets produced, what wavelength, will depend on the semiconductor's material. Some examples of LEDs. Some decorative lighting. A fun and colorful example, LEDs are commonly used for decoration. In order to achieve these desired colors, the key semiconductor material are indium gallium nitride for blue, green, and UV, aluminum gallium indium phosphide for red, yellow, orange, and gallium nitride for blue. Another example of LEDs are car headlights. A rather more recent addition to vehicles, LED car headlights have become a more popular car design due to more visible and bright energy efficient and longer lasting compared to halogen lights. Indium gallium nitride is the most common semiconductor for this, causing the blue-white light. And our last example we had are low power lasers for phototherapy. LEDs are now being used as a substitution for low power lasers in phototherapy protocols, a safer and more economical approach to photobiomodulation, red light therapy that stimulates cellular activity on biological tissues. Aluminum gallium indium phosphide for red color is the most common semiconductor. The science background. Using the combined principles of physics and chemistry, light-emitting diodes are able to operate such as electrons in semiconductors and emission of photons. When the electrons drop from high to low energies, they will emit photons whose energy depends on these gaps. In P to H junctions, the electrons and holes will move across and come back together to produce light. The particle size, energy, wavelength, and electron behavior interactions show how chemistry and physics work together to produce the functions of LEDs. Science LED colors. LEDs are able to emit multiple different colors. The most common colors LED lights can produce are red, green, and blue. In order to produce blue and green light, the particle size decreases, the energy gap increases, and the wavelength will be shortened. Green light is similar to blue light, but it requires longer wavelengths. When the particle size increases, the energy gaps decrease, and the wavelengths are longer. The color emitted is red. How this relates to quantum chemistry. The operation of LEDs is rooted into quantum mechanics and relates to Einstein's photoelectric effect, which shows that light is made of quantized energy packets called photons, and that material can be emitted electrons when they absorb light. Unlike the photoelectric effect, LEDs work in reverse, by using electrical energy to excite electrons which release photons as they recombine with holes, producing visible light. So this is a picture of the photoelectric effect. We see a photon going into a metal, and then when the photon hits the metal, it ejects an electron. LEDs work in reverse, so instead they take in an electron goes in, and they shoot out a photon. And then the conclusion of LEDs. By combining the principles of chemistry and physics, LEDs are able to produce lights of different colors. The color of the light all depends on the energy gaps from when the semiconductors convert energy into photons. LEDs relate to the quantum chemistry course because it explains how electrons transition between energy levels and release photons, which also shows how chemistry and physics works together in our everyday lives. And then this is a list of our sources.